Hello everyone, welcome back to our course in college algebra. Dr. Tom McNamara here, and we are going to continue talking about solving systems of equations. In our previous few videos we had focused on solving systems by substitution. In this video we're going to talk about solving systems of equations by elimination. And the reason is elimination is really the only way to go when you have more than two equations, two unknowns. So if you have three unknowns, you really need to go solve by elimination. So we're going to practice this by looking at 2 by 2 systems, practice it on those, and then we'll work our way up to 3 by 3 systems. The basics of the method of elimination are you're going to add multiples of one equation to another with the goal of getting a new equation that has fewer variables. And we're also going to need to be able to recognize the three cases, the three types of systems. Consistent independent, where you have exactly one solution, consistent dependent, where you have infinitely many solutions, and inconsistent systems, where you have no solutions. So we'll see an example of each. So let's get right into things. And work our first example. So what I want to do is I want to solve this system of equations. 2x plus 3y equals 2. X minus 2y equals negative 5. And we'll solve it by elimination. Okay, so first thing I look at my coefficients of x. I see in equation 1 the coefficient of x is a 2. Down here the coefficient of x is a 1. I want these guys to match up but have the opposite sign. So what I'm going to do is I'm going to take equation 1, I'm going to leave that alone, and I'm going to do minus 2 equation 2. I'm going to do equation 1 and I'm going to do negative 2 times equation 2. 2x plus 3y equals 2. Negative 2x plus 4y equals 10. Okay, so I want you to notice that every term in the second equation got multiplied by negative 2. That becomes a negative 2x, this becomes a positive 4y, and that becomes positive 10. Now, you'll see if I were to combine like terms on the left-hand side here, the x's would cancel. In fact, let's go ahead and do that. Okay. So this is my new second equation. Okay, so now my system is looking like this. Instead of 2x plus 3y equals 2 and x minus 2y equals negative 5, my new second equation is y equals 7/12. Now, the nice thing about that is, well, when I eliminate the variable x from the second equation, that leaves an equation with just one variable. So it's easy to solve. Now, to find x, I'm going to use a process we call back substitution. I take this back up to the first equation, like such. And now I solve for x. So if this equation is true, that means 2x plus 7/4 equals 2, right? The 3 can cancel with the factor of 3 that's living inside the 12 and give me this. So let me see here, what do I get? I would subtract 7/4, and I think I end up getting x equals 1/8 when all is said and done, right? Because if I do 2 minus 7/4, well, 2 is 8/4, so that's 1/4. So 2x equals 1/4, so x equals 1/8. So it looks like this is a consistent system with that solution, okay? So this is a consistent, independent system. Let's look at a couple of other examples. Okay, how about this one here? How about we go and do this? Okay, 4x plus 2y equals 10, and negative 2x minus y also equals 10, let's say. Let's do this example. Okay, so I tend to be pretty systematic when I solve by elimination. I'm always trying to eliminate x. So I look at these guys, that has a 4x, this has a minus 2x. Remember, the goal is I want the coefficients of x to match up but have opposite sign. So if I hit equation 2 with a 2, I can make that happen. So I'm going to take equation 1, combine it with 2 times equation 2. So equation 1 stays the same. Negative 4x minus 2y equals 20. Okay, remember, every term gets hit with this multiplier. Here, you get a negative 4x. Here, you get a negative 2y. Here, you get a 20. Don't forget, every single term, including the thing on the other side. Okay, so the x's cancel. Now, unfortunately, what happens here is the y's also cancel, so the left-hand side is 0, and the right-hand side is 30. This is what we call a contradiction. This statement is not true. 0 is not the same as 30, but this equation is saying it is, so that's a problem. So whenever we have a contradiction like that, so we do the algebra, and we get a situation where the variables all cancel out. If you're left with a false statement, then you have an inconsistent system. So inconsistent system, in other words, there is no solution to this system. Okay? So we talked about how to recognize inconsistent systems graphically in an earlier video. Remember that the situations you can have when you have 2 lines, well, typically your 2 lines are going to cross in one place. But not every pair of lines is going to cross. You could have parallel lines where the lines don't cross. And of course we know that solving a system of linear equations like this corresponds to finding the point where the graphs cross. So if the graphs are parallel lines, your system would be inconsistent, no solution. So this is how you recognize it algebraically. Okay, one more example. In this last one, I want to try this. X minus 3y equals 1. 2x minus 6y equals 2. Okay, so once again, I'm trying elimination here. So I'll take 2 equation 1. Actually, let's do negative 2 equation 1 plus equation 2. All right, because remember, I want them to match but have opposite signs. So I have a 1x here, a 2 there, so I want this to be a negative 2 to cancel out. So negative 2x plus 6y equals negative 2. All right, hit that with a negative 2, hit this with a negative 2. Don't forget that every term with a negative 2. 2x minus 6y equals 2. Okay, so we have set up the scenario where the x's are going to cancel out. Once again, it happens that the y's cancel out as well. So the left-hand side we get 0. The right-hand side we also get 0. Okay, so there's a similarity to the example that we just saw, but there's also a difference. The similarity is that the variables all canceled. The difference is that in the previous example we got a false statement. This is a true statement. So this system is consistent and dependent. Okay, consistent, dependent. So there are infinitely many solutions to this system of equations. Okay, the way our textbook writes the solution set in cases like this is we're talking about the set of all pairs of numbers x, y, and then you just take one of the equations, typically the first one. All pairs of numbers x, y such that x minus 3y equals 1. Okay? And the reason being is that these are actually just two different versions of the same equation. Notice if you take equation 1 and hit everything with a 2, 2x minus 6y, 2. Equation 2 is actually just equation 1. It's equivalent to equation 1. Everything's been hit with a 2. So if you have a pair of numbers that satisfy the first equation, that pair of numbers automatically satisfies the second equation. Okay? So any point that's on the graph of this first equation will also be a solution to the second equation. So that's why we have this language right here. The equations are dependent on one another. So let me do a little diagram here about the types of scenarios we can have. Okay, so two things. Your system can be consistent, or your system can be inconsistent. Okay. Now, if our system is inconsistent, it has no solution. We can recognize that we have an inconsistent system algebraically by all the variables cancel, and we are left with a false statement. Okay, all the variables cancel, and we are left with a false statement. Now, if your system is consistent, there are two flavors. You could have an independent system or a dependent system. If your system is independent, you have a system of independent linear equations, then there will be exactly one solution. That's the case where we have two lines and they cross in one spot, and the coordinates where those cross is the solution to our system. It could turn out that your system is dependent, in which case you have infinitely many solutions. And you can recognize a dependent system if the variables cancel and you are left with a true statement. Okay, the variables cancel and you are left with a true statement. In that scenario, you know that you have a consistent, dependent system. Okay, so be able to recognize these three different cases, both algebraically and graphically. Here, lines cross in one place. Here the lines actually coincide. Here the lines are parallel. And of course we've got the algebraic conditions written right here. Okay? So the method of elimination. In our next video we're going to look at writing some word problems that lead to systems of equations and dealing with 3 by 3 systems.